Hello everyone, welcome to this lecture. This is first of the lectures in the series of online lectures being offered by CC Tech, short form for Center for Computational Technologies. I'll be taking you through the next 45-minute session to explain to you and to introduce you to give you a brief overview of what CFD is. Well, let's be clear about what we are expecting from you and what you should expect from us as part of this lecture. Well, we are not expecting you to be very well conversant with CFD terminologies, but nevertheless, an engineering background in mechanical, aerospace, or chemical is desired, and we expect you to have gone through the basic course in fluid mechanics and are familiar with engineering mathematics. What we would be explaining to you through this lecture is to give you a more technical view towards computational fluid dynamics, not just the regular plots and animations which you are familiar with. By the way, CFD is not just unrealistic animations. We'll be showing you how technically sound and relevant the different figures that you are usually must have seen in different portals, web portals, on websites of different software companies as well as consultancies. So we'll be introducing you to these the technical view which is behind these specific images. That's what CFD is. It's actually solving the real equations. So in this context, we'll be introducing you to what the basic terminologies are, and this lecture should be able to deliver to you a fundamental knowledge of what actually modeling and simulation does and how analysis of different designs, different product development can be enhanced through such a simulation based studies. So that's what we'll be introducing you to, and I hope you'll be familiar with these terms and can take forward the lectures in the subsequent lectures that are going to follow. You can follow this on the basis of this fundamental lecture. Just an overview of the presentation. We have CFD analysis terminology that I mentioned about design, model, simulation, and analysis. We'll be having a brief insight into fluid flow and heat transfer. My focus today would be to give you some basic definitions of these terms. Computational flow dynamics or fluid dynamics. Well, there's a lot of discussion about this, but I would say CFD is better described not by the conventional name computational fluid dynamics, but rather flow dynamics, because you can capture fluid flow as well as heat transfer flow, or so to say flow of any phenomena can be captured computationally, and that's what we are analyzing in CFD. What this is, the three-step procedure, which includes geometry creation and meshing as part of pre-processing, solving the equations which govern this phenomena, which are usually encountered in flow dynamics, and doing an analysis of it based on post-processing. We'll see some of the applications of CFD, and in another lecture, which will be a demonstration of using Fluent as the solver, we'll be discussing about how to do a mesh import using the solver and doing some simple post-processing steps. Well, to just get familiar with the terminologies, we have design being defined in this way that we have the given geometry, given problem, and from this we try to take down all the design parameters. With these design parameters, we actually end up making a model. Now the model can be in different ways. We actually make a real model of it, of your given geometry or given problem. Model also includes, by the way, mathematical model. So you can have your phenomena being described through mathematical terms. You can have your geometry defined through mathematical terms, and that's what is actually used on a computer to represent geometries, to represent phenomena. When you end up solving them, that's what is called simulation, that you solve you solve the equations within the constraints of the boundary conditions and geometry and initial conditions. That's when we perform a simulation. So before we actually make the physical um, geometry or physical model and we try to do experiments on it, we are actually able to do some simulations. And with this simulation results, the data which is generated, it's a huge amount of data often, we try to put them and give some color coding, and we are able to do some analysis. We are able to predict quantitatively as well as qualitatively what the design looks like. And it's a computer, which is a device which we use to perform this analysis. So the computer's task comes primarily at the simulation stage. That's what we'll be learning more specifically in this course. And well, if you can use a simple calculator or a hand calculation, anything that compute this whole process would be enough to perform this simulation based analysis of a design, having gone through the physical and mathematical model. Well, first of all, let's start with the fundamental, which is the fluid flow phenomena. So fluid dynamics actually is a fluid under motion, and it is governed by a certain set of conservation equations, because we are dealing with classical mechanics here. We're not dealing with the quantum mechanics or particle physics. We are dealing more at the level of classical mechanics, where things are conserved. There is no conversion of energy into mass and the other way around, but we consider mass, momentum, energy to be conserved. When I say momentum is conserved, it can be that, let's say, there is an additional force being acted upon, but that turns out to be the rate of change of momentum, which is just force. So these three quantities, mass, momentum, and energy, if they can be solved entirely, we can define any fluid flow. And these conservation laws are formulated in the form of equations, which we try to actually solve, and that's what simulation is all about. But leaving aside simulations, if we were able to solve it using even simple pen and paper, the aim of doing any fluid flow analysis is twofold. One of them is to find out things like what's the effect on the boundaries, what's the effect on flow boundaries, what's the effect on wall boundaries. Let's say when I say flow boundaries, that's where any fluid or any quantity that I'm trying to conserve can pass across. And when I speak about wall boundaries, things cannot pass across such a boundary. So for example, heat can flow across a wall, but fluid cannot flow across a wall. It is interrupted in its motion. So we are interested in calculating things like torque, like force, like pressure drops across the inlet and the outlet. We are interested in finding out what's the mass flow rate for a specific pressure that I am applying at the fluid at the inlet side. So these are the effect on the boundaries that we're interested to have an idea about. The drag on a plate or in a car or any object we are trying to analyze. So such quantitative prediction is an aim in any fluid flow analysis. And the other one, of course, we are looking for flow visualization. We are trying to find out where the flow is getting separated, where there is a separation bubble, where there are secondary flows getting developed. Because of the secondary flows, if there is any adverse effect on the primary flow, and if there are some recirculation zones, that's a usual candidate in a room if you are doing a heat and heat transfer and ventilation studies, HVAC analysis, heat ventilation and air conditioning studies. They are very much interested to find out where there are recirculation zones. That's where the temperature is supposed to rise up usually, and the flow is not really helping that the heat can get dissipated. Or I mean, if it's about heating a room, then it's not really being the convection driven flows are not being utilized well. So these are the twofold purposes of fluid flow study, which is to find out the effect on the boundaries, which can be flow boundaries or wall boundaries, and we are also interested in doing some flow visualization. Now we're going to look at later on the advantages that CFD offers, because it's an introduction to CFD, as you can see. But we will see that this flow visualization is a very important aspect where CFD scores over many other phenomena that we usually have. So we have had people like across the centuries who have contributed to fluid mechanics. We had people like Archimedes, Newton, who had a great contribution in mathematics. In fluid mechanics, it's just in optics that he actually failed. But otherwise, as far as our course is concerned, he has had a great contribution to what we are learning today. People have gone on. Archimedes, of course, I guess you know that it's before Christ that he existed, and he gave in very interesting phenomena called the buoyancy effect, on the basis of which you can do a lot of natural convection studies nowadays. It's a very challenging task in CFD nowadays. We had people contributing a lot for the mathematical modeling part. We have people like Leibniz, Bernoulli, Euler, Navier, and Stokes. This name will be familiar to you and will come up very much in fluid mechanics studies. So we have these guys contributing a lot to the mathematical model, and actually in the last, so to say specifically the last 2 centuries, the treatment of fluid mechanics has been primarily mathematical, which has helped also a lot of mathematicians to contribute. And we had people like Reynolds who gave in the nice number called Reynolds number, which helps us to determine whether the inertial forces will dominate the viscous forces and end up causing the flow to be turbulent. We have also Prandtl, who has contributed especially in the early part of the 20th century, and his Prandtl's boundary layer theory is very helpful in predicting more accurate drag on airfoils. This was one of the major contributions, and of course he had a great contribution in heat transfer as well, and that's why we have something called the Prandtl number, which is a relative measure of the velocity boundary layer and the thermal boundary layer. Taylor series expansion, again another name which you would come across if you're dealing with numerical methods, especially the finite difference method. So we have had people contributing in fluid mechanics and solution of fluid mechanics mathematical models and formulating the models across the centuries, and we are living in a time when the software firms or software packages have exploited all this work which has been done across the centuries with the advancement of computational speeds now. So let's speak about more about fluid flow, leaving aside CFD. Well, fluid flows are encountered every day. It doesn't have to be in our only in the daily life that we encounter. Actually, if we ask ourselves anywhere in the universe, can we find any process where fluid flow and heat transfer is not involved? I think we'll be struggling for an answer. I guess you got it right. Yes, it's everywhere. It's everywhere in the universe. Even if you don't find exactly a fluid flowing, you will surely find a lot of heat transfer being existing in different parts of the universe. And more specifically on our Earth, we have weather and climate changes, which are very much a function of such fluid flow driven by heat transfer and pressures, of course also assisted by the motion of the earth, the rotation and the revolution around the sun. So we have different temperatures which cause a lot of these flow phenomena. We have fluid flow and heat transfer applications for as high as the air for aircrafts, as low as the sea on the surface ships, and of course under the sea in submarines, and also on the land in locomotives and automobile sector. So we have them in recreational activities as well, especially they are very much interested to reduce the drag so that they can increase the fuel efficiency and the performance of cars or bike riders or those who are cruising through the sea for water sports as well. Overall, we are dealing with a very beautiful phenomena called fluid mechanics. So that's the reason why we are dealing with fluid mechanics, and we're going to go through more specifically how fluid mechanics has been modeled and captured and done on a given computer, apart from the analytical studies. But let's look at how people try to analyze fluid mechanics across the centuries. First of all, as I mentioned, a lot of things were done on paper. This was analytical fluid dynamics. Before the computers really started coming up, the computer that we know, the fast ones, the desktop computers or the laptops, people were doing a lot of calculations using hand calculations, using pen and paper, and the usual process that they used to follow was, well, they do a free body diagram, they make a free body diagram, they try to use some methodology, some smart engineering assumptions after having listed down the mathematical model. With, with those assumptions and approximations, and in some cases real simplifications of a three-dimensional complicated geometry into a simple two-dimensional or one-dimensional analysis, they ended up doing an integration of these equations, setting up the constraints in the form of initial and boundary conditions to find out the constants of integration, and ultimately getting values at discrete points, and that's where they could end up having a nice results, get plots, get the force variation across a plate. So this is a very simple problem of drag on a flat plate, which you would find in regular fluid mechanics textbooks, using a finite volume which is generated around the streamline, where the velocity is constant from the inlet to the outlet, and they could find out a correlation, or I would not say a correlation, an exact integral equation for finding out the drag d on this plate. Well, that's analytical fluid dynamics. That's AFD, which is bound to be limited on such complicated geometries as this that we are seeing on this screen here. It's not just geometry, but in more often than not, actually, we are limited as far as defining the exact physics in terms of mathematical equations are concerned. So we have a general transport equation, which I'll be discussing, which I think my colleague will be discussing more specifically. General transport equation for a quantity phi, the quantity phi being different values representing different equations. To actually solve them on real geometries is quite a challenging task. So if we don't want to deal with actual calculations, we have another process which is called the experimental studies. But before that, we can see that analytical fluid dynamics is quite limited for geometry's sake as well as physics sake. So we have experimental studies. We have we have a scale down model, often based on engineering dimensional analysis. It's not arbitrary, it's based on dimensional analysis, that we create a prototype of the product, a scale down laboratory scale model. We perform an appropriate experiment under conditions which would reflect what would happen in reality, and we put in a lot of probe points. Now, when we put these probe points, that's one of the limitations, that actually we end up introducing a lot of disturbances in the flow. And often it's quite difficult to manufacture a real prototype and to be able to perform such an experiment in a laboratory setup, and the cost also goes up. So we are again not able to solve the typical issues that we are bound to face, that is in terms of time, cost, and feasibility. Analytical fluid dynamics is surely we are able to find out some solution, that we are able to capture the actual physics in some cases, not on the real geometry often, but on the scale down model. But we are having problems with cost and feasibility, and that's why we have CFD. Now compare this heat sink performance, which the image that you see besides your on the right side of your screen. Now in CFD, what we are doing is we have the mathematical model clearly defined, that's the physics, and this physics equations, which are usually partial differential equations, are being solved through numerical methods. They're not being solved analytically or actually through real integration, but we are using some numerical methods to with with the assumption that we can neglect some higher order terms, or we can use a computer to solve them. We end up having a CFD result, a result which is a numerical solution of your physics. The advantages are quite very many. We have a low cost simulation. Now here is the word simulation that comes, that we are able to solve these equations. It's a low cost solution. We are able to do a lot of analysis within a very short period of time. That's because we don't have to actually make the physical models, but it's a short variation in the some parameters on the computer, which because the computers are quite fast nowadays, even a desktop computer can perform the task of quite considerable amount of complexity involved in a given problem. CFD is able to solve it. So we are having low cost, we are having quite good speed, and additionally we are also able to have comprehensive information, and that's very important aspect compared to an experimental study, that we are able to have information not just at selected points, but we are having them at a huge number of points. That's on the different mesh elements I'll be speaking about later on. What is a mesh? Now these are different probe points within your domain where you want to get the results. Now that's what the power of CFD is, that you don't introduce any errors by introducing any probe points, but we are able to get data at many more points as compared to an experimental study. if we try to compare experiments and simulations, this is one of the very great advantages, that we are able to have a very clear quantitative as well as qualitative. Of course, the images that you see are usually the qualitative studies of a given system based on CFD, but we are able to have qualitative and quantitative analysis using simulations. We are able to have not just one or two or few quantities being analyzed, but we are having several quantities being analyzed with high resolution, not just at limited number of probe points. And we are often able to model the real geometry. If the physics is clearly defined, we are able to model the real geometry, and we can perform idealistic simulations. We can also simulate ideal conditions and the realistic operating conditions. Nevertheless, of course, there are errors in both cases, and we have to be aware of the errors before handling any tool so that we can count on the reliability of a given tool for analyzing a given problem. So we are having problems in experiments because of measurement errors, flow disturbances. In CFD, on the other hand, it's often at the level of the user. That's also in experiments, of course, the user can make mistakes in measurements, but in CFD, the errors are often at the level because of lack of knowledge of the user, or let's say the user is not very well familiar with which models need to be included into the given simulation, a given setup of the problem. So that's what we are trying to help you with through this course, that we are trying to improve your knowledge of CFD tools and their capabilities in including different physics. And CFD can give us good results, or simulations can give us good results if we are well familiar with how to do an appropriate model. Of course, there are also some errors on the part of the computer, or also the numerical schemes. Again, numerical schemes we can try to improve and we can reduce the errors. But of course, we are using a computer usually which has limited precision, and this error we cannot completely get rid of. But we can see that most of the cases these errors are quite insignificant compared to the insight that you obtain through simulations. A snapshot of what experiments and simulations differ in which points we can see that experiments and simulations, they have their advantages and disadvantages, but simulations score over the experiments often because of being cheaper. Of course, it's a relative matter. If the manpower gets more enhanced, of course the cost of the employee also increases who will perform the simulations. So it's not always that it is always cheap. The software licensing fees are also a challenge, but often much cheaper than actually making many prototypes and performing experiments. Besides, we are getting comprehensive information and quite fast results compared to real experiments. But CFD simulation results are not always 100% reliable. We have to be aware of what are the reasons, what are the circumstances under which these things are not reliable, and we'll see this, that the reliability is in question because sometimes at the part of the user there's too much of guessing as far as the constraints of the problem are concerned, or too many approximations involved to reduce the timeline or reduce the complexity of the CFD problem even. And that's where the lack of accuracy comes in. Too much of guessing on the part of the boundary conditions or geometrical simplifications, or also because of the computer, which can result in lack of accuracy because computer has limited precision. And of course, if the user is not well familiar with the mathematical model that needs to be included into your problem, there can be also modeling errors. We'll be looking at it more exactly in the subsequent slides.